Yeah, let's continue with the end of last lecture. Yeah, so beginning here, you see this one because we just according to the face of the road. So that's why the histogram you will see, suppose the AV number to be road, the outcome will be almost 1/6. So here is we really do the sampling. So that's what we call empirical distribution. So we only do 10 times. So you can see every time you run, okay, so they are not really 1/6. They vary the result, right? Sometimes earlier, yeah, that one actually pretty close. Yeah, but sometimes they are not. Okay, so then they are, we call empirical distribution. So because you only run 10 times, so like this one, you have 5. Actually, I think they have at least like 5 times. They show 5. Okay, no 1, no 4. But again, then we try, if we make our sample, we rolling the dice 1,000 times. Yeah, we do it again. 1,000 times. Yeah, not really 1/6, but still, yeah, at least much better than before. Okay. Then you can see, yeah, here that's what we call empirical distribution because you observe how many times you do. So continue. We do, how about 10, this one is what, 100,000 times. Okay, you run 1 time. Wow, super close. Again. Okay, so that's what we talk about empirical distribution. Actually, your empirical distribution, we came from the observation result, right? So your outcome chance is according to the period of the time, according to your result. So if you only rolling a dice only 10 times, the outcome for each possible number, you see this one even doesn't have the outcome for 1 and 4. Okay, so the 5 actually is more than 50%. But then we do 1,000 times. Yeah, they kind of closer, at least the difference is not that much. Then if you do 100,000 times, yeah, actually they kind of equal. Okay, so this one is we call the law of large number. Okay, so we back to see. Yeah, so that's what we call the empirical distribution. All the observed unique value, your result. Actually, your result will be proportion of time for each value appear. According to how many times you observe, actually they're quite different, right? Then we find out if you have large random sample, more, you observe more. That's what we call the law of average or law of large number. If a chance experiment is repeated many times, like earlier, and we do rolling dice 10 times, 1,000 times, 100,000 times. If you do repeats many times, independently and under the same conditions, yeah, of course we can trust Python to do that. Okay, so then the proportion of time that an event occurs get close to the theoretical probability of the event. As you increase the number of rolls of a die, that we did earlier, we show you, the proportion of time you see the face with 5 spots get closer to 1/6. Okay, so that's the output earlier we see. So you can see you only run 10 times. Wow, way far away from the theoretical. So here is the theoretical result, right? So supposedly every number will be 1/6 chance. 10 times, well, way much different. 1,000 times, much closer. Of course, you do a big number. Yeah, this one is 100,000 times. They're really close to 1/6. So this one is we call the large random sample. Okay, so as long as you repeat many times, the distribution of a large number of sample size, they will close to the population. So usually we see the population kind of like theoretical probability of the event. So that's why when we want to observe, we call empirical distribution of a sample. If the sample size is large, then the empirical distribution of a uniform random sample resemble distribution of a population with high probability. So your sample size is large, they will be very close to your distribution, will close to the population distribution. But how big it is, yeah, so then we have many different reasons what is exact good number to choose is large. But before that, let's see when we see the demo from the Python. Yeah, so like earlier we said, right, your sample size is big, they will kind of closer to your population distribution. So that's why we use the united. Earlier we create this sample. Okay, so remember this united flight delayed. We have almost 14,000 row. Okay, so this one actually kind of is good enough. We call that our population. Okay, so then you will see the histogram. Okay, so we have our, the reason we choose the range, you will see because the minima for the delay is they take off early. Okay, so then the maxima, oh my god, 580. 580 is what? Almost 10 hours. Okay, so that's why we got the number kind of the being arranged like this. Okay, so then you can see the delay. So you can see the distribution for the all 14,000 flights. Their delay is they most close to 0, right? Okay, so they do have some percentage on time. Okay, so then we can say the most population is close to on time, but you still have crazy delay as well. So that is kind of the distribution for all the data, right? So that's our population. Okay, so then let's see here. If according to this population, okay, if from this table we try to do the samples, okay, so then we see what's happened. Okay, so this one, because we have united table, so we sample with only 10, we only choose 10 flights. So we're using the same thing as earlier we create. Okay, so then you can see here. Okay, so compared to this, so let me temporarily remove that 3 columns so you can see compare. Okay, so if just 10, yeah, actually not very alike, right? So you can run more time, but still because the 10 is too small. So this one kind of right, this part is similar, but they don't have the rest of that. Okay, so then you run again. See, even this one is even not very close at all. Okay, but this one, because you only choose size is 10. So how about we sample with 1,000? Okay, so then here, let me remove. Yeah, I think it's that I cannot remove. I just do this way because you can see 3 of them. Okay, if you have 1,000, yeah, the shape is really close to what we have, right? So that's what we mean. When you have one, let me add one. Yeah, you can add one more too. Okay, so that's why here we have the population distribution. We only choose sample 10. Here we choose sample 100. Yeah, kind of little, but not very good enough, but at least better than 10. But if you change to 1,000, they really kind of more like that, right? Of course, we can change to 10,000, but 10,000 kind of only 1/14 from our the population. Yeah, let's see. Okay. So this one. If you want to add one more 0, yeah, of course, there are even more to the population. Okay, good. So you see from what we're showing here, according to the different sample size, so we have 10, 100, 1,000. So that you can see when the sample size to 1,000 is large, then the empirical distribution of a uniform random sample, they will kind of the distribution will be very close to the population. Then, yeah, they will be very much closer to the population. Okay, so that's we call the large sample data. But we back to see the graph here. We see the no matter is the 10,000 sample or the population. So now the next topic we want to talk about is statistic. Okay, so just see the population of the delayed. If we want to choose one number, only one number to represent our population. Okay, so what you can do, pause the video and think about that. So discuss with your classmates or anything, or think by yourself. So that's why earlier I told you, if I want to have only one number to represent those delayed, yeah, we back to the statistic. I believe earlier you guys think about some terminology about the statistic. Yeah, we can using the mode. For example, you see here, the mode actually is when you have all your population. So then the highest frequency show. That's what we call the mode, because they have highest frequency show. So then we can maybe use this number to represent the delayed. Or you have median. So median is we have all our data, we from the small to large. We make them in an order. So the median will be in the middle of the location. Okay, so this one, so yeah, earlier this one, because you can see they are really from small to large. But just one thing is they're using the percentage to show. The one thing is when you need to find your median, you need to have exact number put into the order. So median will be, for example, if you have 100 number, your median will be the 49, the 50, 49, 50, the average. So usually the median we want to use the number is kind of odd number. So if you have 101 or 101 number, actually the middle number will be 51. Okay, so that's the median. Or sometimes depends on your distribution. Average may be good too. So you can see this one, maybe we can just got all the data, then we just find the average of the delayed. So then you can use that to represent. But which way is the best way to represent? It all depends on your population, on the nature of your population. So that's why when we talk about we want to get a good sample data, that means population, a lot of the time we do have our data set. But sometimes you want to really do the worldwide. You cannot get all the number, right? Okay, so that's why sometimes we only can get the sample data to kind of predict or think about the population possibly will be like that. So how to make sure our sample data and can represent the population? If they can, so maybe specific value from the statistic, they can represent from our, using that the average from our sample data. Then we can use this average to represent the population. Okay, so that's we will all talk about the statistic. So this one we will talk about in the next lecture. And we will talk about more in detail in the next lecture. But here I just want to show you, right? So very quickly, you see you can just using the NumPy function median. You passing the column delay. You see they give you the median. Okay. Or you see here, if I just sample, just got 10 number, then you will see, oh, their average is -2. Okay, so that's why here you will see the sample data, that we have the median function. Okay. Here I just want to show you, you see from your NumPy, we have average function, we have median function, so that you can all use that for. Okay, so then I just want to quickly to show you, if you just want to median to represent, right, when we got the median, this one actually is for the population. Okay, but if you only get 10 samples from there, yeah, you see the number actually every time they will change, but they are not really quite close to. So more we will talk about in the next lecture.